So we're going to continue on with complex numbers, and we're going to talk about a couple other ways of looking at complex numbers, and then also solving an equation where we get complex solutions, and then one application that it's important, but I'm not going to test you on this application, but I like to give people a real life application of complex numbers. Okay, so what we're going to start with here is graphing complex numbers. Now, this is one way you can kind of look at them, and I'm just going to throw a graph up here real quickly. And if we have a complex number, z is equal to a plus bi, you can think about plotting this point, and you can think about plotting it as x equaling a and y equaling to b. In other words, what we think of is that the y-axis is what we call the imaginary axis, and the real axis is what we call the x-axis. And so let's just look at two quick examples here. We don't need to spend too much time on graphing. We will come back to this graph here and these two examples in a second. So let's look at z is equal to 2 plus 3i. So this is, again, just like kind of plotting regular points. So 2 on the real, so I'd go over 1, 2, and then 3 on the imaginary, so I go up 1, 2, 3. Then I just put a point right here. So that's the complex number 2 plus 3i. And then we can do a similar thing here if we have, for instance, z is equal to negative 3 minus I. Well, that would just be going to the left 3, 1, 2, 3, and then down 1. And so that would put a complex number right there. So that's really all there is to graphing complex numbers. It's just plotting points like we're used to. Now, the next thing I want to talk about, though, is what's called the modulus of a complex number. Now, the symbol looks like the absolute value symbol. So we have the modulus of z. It looks like absolute value, but it's actually called the modulus. This is equal to the square root of a squared plus b squared. Notice there's no I in there, just a squared plus b squared. So let's go ahead and do an example of what this is here, and we'll talk about why this is what we use to represent what's called the modulus here. So let's look at the modulus of 2 plus 3i. So this would simply be the square root of 2 squared plus 3 squared, which would be the square root of 13, which I'm going to go ahead and write as a decimal number here. Square root of 13 is approximately 3.61. Okay, so what is this modulus here? And I mean, as I said, it looks like absolute value. And it actually is, I think, if you think about absolute value the correct way, it is related to it. Remember, we talked about this in an earlier video. Absolute value, a lot of people like to think of it, oh, it just makes the number positive, or any negative number becomes positive. And well, technically that's an okay way of thinking it for computational purposes. It's really not the definition of the absolute value. The absolute value, a true, in my opinion, mathematical definition, is it's the distance from 0 the number is on the number line. Well, how does that help us in order to relate it back to here? Well, we don't have a single number line, we've got a graph here, but we do kind of have a 0. The 0 that we're looking at here is the origin. And so we're saying, well, what distance is this point then from the origin? Now, there's lots of ways you could maybe do that distance, but if we're talking about, well, what's the shortest distance? Shortest distance would be just a straight line. So if I were to draw a straight line here connecting this, the length of this line is 3.61. In other words, it's our modulus. And so, and you can actually see why that would work here, because if you think about this, what do we have here? We have a right triangle. this has got a length of 2 and a height of 3, and using Pythagorean's theorem, you could get that this would be the square root of a squared plus b squared, square root of 2 squared plus 3 squared. So that's exactly where it comes from. So modulus is still talking about a distance. It's talking about a distance from origin. It's just a different terminology, and it's something you have to be careful with, because when you're talking about something, I mean, this isn't just an absolute value. And so let's just do one more quick example here. For instance, let's look at the modulus of 4 minus 3i. So this would simply be the square root of 4 squared plus negative 3 squared, which is the square root of 16 plus 9, which of course is just the square root of 25, which is 5. So not really too much difficulty with modulus, but it is something that we do need to be concerned about at times. Alright, so then let's finally look at solutions here and square roots of negative numbers. So, square roots of negative numbers. For instance, let's look at the square root of negative 5. Well, what we can write this as, this would be the same thing as the square root of negative 1 times 5. And I'm belaboring this a little bit on this first example. So that's the same thing as the square root of negative 1 times the square root of 5. But then what is the square root of negative 1? That's just I. And so we'd have I times the square root of 5. Now when you have a square root like this, we typically write the I out in front to make sure that you don't mistake the I being part of the square root. So we typically would write I times the square root of 5. Now another one here, if you have, for instance, the square root of negative 9, this would be the square root of negative 1 times the square root of 9, which would be I times 3, which we could write as 3i. Now, as it turns out, it doesn't matter if you write I times 3 or 3i, but as I said, for square roots, if we wind up with a square root, we typically write I times that square root. Alright, so let's look at this as far as solving a quadratic equation here. So let's look at a quadratic equation. 4x squared plus 16x plus 17 equals 0. So we'll use the quadratic formula, and quadratic formula, of course, is x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. Again, notice I wrote it out, even though I already have it memorized. I wrote it out again and even talked it out again as I wrote it out. Alright, so then we're just going to do our normal substitutions. So we'd have x is equal to negative 16 plus or minus the square root of 16 squared minus 4 times 17 times 4, all divided by 2 times 4. And so this would be negative 16 plus or minus the square root of 256 minus 272 all over 8, which would be negative 16 plus or minus the square root of negative 16 all over 8, which would be negative 16 over 8 plus or minus the square root of negative 16 would be 4i over 8. And so we get negative 2 plus or minus 1/2 I. Now, one thing to note here is that we have two solutions, negative 2 plus 1/2 I, negative 2 minus 1/2 I. And we should notice that these have something in common here, or something about them. These are complex conjugates. And this is maybe a star here. If the quadratic equation has real numbers for A, B, and C, any complex solutions occur in conjugate pairs. Alright, so this really marks the end of the material on this, but I want to give you an example of application or use of these complex numbers. Now, I'm not going to go into a lot of detail, but I'm going to draw you a couple basic circuits here. Now, the first one is just going to have a voltage source and two resistors. R1 and R2. Now, to analyze this circuit, you might look for voltage across the resistor, current through it, and to do that requires something called Ohm's law, which some of you may know this. It's voltage is equal to current times resistance. And then we could use that and some other rules to analyze the circuit. But it's basically just an algebra problem. It's a fairly simple algebra problem once you know some basic circuit analysis. Okay, so what's the big deal? How does that involve imaginary numbers? Well, it doesn't. That one doesn't. But there are other circuit elements that we use besides just resistors. One of those circuit elements is called a capacitor. And I'll draw a circuit with a capacitor here. Now, I'll just call this R and then C. Now, if we want to analyze this right now, we could. Actually, we probably couldn't in this class because this requires something called differential equations. So if you take calculus and you move on from calculus, there's some class called differential equations, and you need differential equations to analyze this, which they're not honestly, that hard. Some people go, oh, it sounds really hard. Well, it's relative. It's hard now for us because we don't have all those tools available to us, but once you get to a differential equations course, you'll be ready for it. Alright, but it would be nice if I could just approach this as an algebra problem. And I can, because there is something we can do is we can convert this to an imaginary thing. And what we do to convert it to imaginary is we have this here, plus, minus, so the voltage source. Nothing happens to the resistor, but then this capacitor changes the value. So this is still going to be R, but the capacitor, we're going to change it to a value, and why we change it to this value is more geared for course in circuit analysis. So this capacitor value would change to 1 over 2 pi f. F is the frequency, C is still the capacitance, it's the same C as here, and then times, notice here, times this imaginary number I. And now when we transform it to a problem like this, we don't have to do differential equations. It just becomes an algebra problem. Yes, it's an algebra problem with complex numbers. And you might say, well, why were we interested in that? Well, there's another reason. If we use differential equations, this is analyzing the circuit with respect to time. Like, what is the circuit doing at 0 seconds, 1 second, 2 seconds, 3 seconds, so on. This way, if we convert to imaginary numbers, we're analyzing what the circuit does with respect to frequency. So what happens if the voltage source is 60 hertz, 100 hertz, or 1000 hertz? And one of the reasons you're interested in how frequency affects circuits is because if you're using a cell phone or anything, those all operate at a particular frequency. Your frequencies for cell phones is in the gigahertz range. Or if you listen to the radio ever, those FM is in megahertz. And so those are all frequencies. So if you like essentially if you like any of your electronic devices, you have to like imaginary numbers, because analysis that we do on those circuits that control your electronic devices use imaginary numbers. So that's my little plug on the importance of imaginary numbers. Right now, as I say, they seem a little odd, but they do have a wide variety of applications, and especially in engineering. But other fields as well as the sciences use them a lot.